In the previous segment, we talked about the general introduction of the full course or at least this portion of the course of strength of material. Now, and I also told that we will be going towards discussing the axial loading, that is the pulling and the pushing. And I also told that that the stress and the strains are the major ingredients of our discussion. So, before exactly getting into the axial loading, we will take 5 to 10 minutes to discuss stresses in a very preliminary way. So, and then we will get into the detailed discussions of stress and stress tensor in a later section. Okay. Now, because this concepts of stresses will be useful in discussing our axial loading to start with. Now, coming to the concept of stress. First of all, when the concept of force was already there, then why did we require even the concept of stress again? Okay, because this all of you know that stress is nothing but force per area, right? So, anyway, this force, the concept of force was existing, then why did we require another concept just by dividing the area on which it is applied? The point is, any material, it does not fail because of this, it fails because of this. Why material? Means for that matter anything, the absolute value of the load or the deforming agents strength, okay. So, which is the force basically. I am telling this because that force could be any type of things. For example, twisting, it is a different kind of effect. So, like that. So, now, so whatever it is, so the deforming agent's strength is not the only thing which decides about whether the material on which it is applying its strength will sustain it or fail. Okay. It depends on this stress. That means you must have observed, right? Suppose you pinch yourself with a pin. Okay. Now, the force which you are applying is very small, right? Not even say maybe 0.1 Newton or something when you start feeling the pain. Okay. But then the same force, if you just apply through your finger, you are not feeling the pain. The pain is coming because something is failing there, the tissue. The tissues are telling your brain that they are about to fail at least. Now, that information that I am about to fail is coming from the stress, because when you are pushing or pressing by your finger, this area is more, though the force is even more, but the area is so huge that the stress on the tissue, it's not a big amount and the tissues are not so concerned. But as soon as you take a pin and try to pinch yourself, think about the area of the tip of the pin. Now, the force is, though it is small, the area becomes so small that the stress increases, and then the tissue starts complaining that I am about to fail. So, that means this is of concern actually, not this. Obviously, this is a function of force, so it is of concern, but at the end this is what is going to decide whether something will fail or not. And that is why in fact all the things which we are going to study, we are concerned with stresses. And the reason being to tell that whether something will fail in a given condition or not, because engineering is all about design, some equipment, some bridges, some houses, so they should not fail. So, that is the idea. Having talked about that, one more thing, what is the difference between, because pressure also you know that it's force per unit area, but then how is it different from a pressure which you know? The difference is, as you know, pressure, when you talk about it, it's inside a fluid, okay, and it's a scalar quantity. So inside a fluid, when you are talking about the pressure at a point, it acts or its value in all direction are same, okay. The pressure at a point means it's a scalar value and its value in all direction, whatever direction you look from, the value of the pressure is same. Whereas stress is a much more complex thing, as I said in the previous section, that we are going to define stress as a tensor. So tensor in a way is like, as vector are more complicated or complex than scalars, tensors are even more complex or complicated than vector. So you just imagine that pressure, though it's a force per unit area, it's a scalar, whereas the stress, it's not even vector, it will be a tensor. So that means and because the solids and liquids, if you get into more detailed, that means if you consider the viscosities and all, even liquids will be able to see these kind of stresses. That means they will be able to, you know, resist not only pull but also sliding, okay. Whenever such kind of ability comes into the material, that they are able to resist sliding between their respective sections, then a single value, a scalar value of force per unit area is not sufficient, and we will have to get into more number of numbers to describe what actually is happening when a particular force is applied, because everything will have directions, okay. So we will see a lot of them. So that is what I am saying. In this segment we will discuss stress in a very simple, in a very preliminary way, and we will, but we will define some very important terms in this segment, but we will get into the complete details in the segment 2.1. Okay. Now if I say that what types of stresses will in general be of concern to us in this subject. Now they are, one is the normal stress, the other one is the shearing stress, and the third one is maybe the bearing stress, okay. Now what these things are, or how do you define them? So what we will do, we will take up a very simple example which will use your knowledge of trusses in a way, and then we will see what exactly these terms mean. For example, suppose you have, you know, a simple truss like this. This is one bar or member, and this is say another member, and these are connected through pin joints over here, and similarly here to the ground, okay. So here it's connected to the ground, here also it's connected to the ground, and what you have done is you have applied say something like this, and you have applied a pressure or force P here, and then you know how to figure out the forces which exist in these members, because it's a truss, so you know that all are two force members. So that means if I give some names to these points, say A, B and C, So now if you consider the bar AB, okay, so you know that it's going to be a two force member, and maybe tensile force will exist in that. And similarly this one will be so this one AB, and say suppose this one I talk about, so this one will be say under say compression, okay. So some force, say F1 and F1 and F2 and F2, and then you know how to evaluate them in terms of this force P and the geometry of the truss. Okay, the point of what I am trying to make is you had calculated the force in when we discussed about trusses, but what about the stress, the normal stress, the first one of our list, you remember, the normal stress. Now this is defined by this force which is acting axially divided by this cross sectional area, okay. If this cross sectional area is A, then this normal stress, which is generally defined as a sigma, I'll say normal, okay. Sigma n will be nothing but F1 over that A, I'll say A1, because if this member is having an area A, it's A1, and similarly if this member is having an area A2, that's A2. So sigma n of the first member will be F1 over A1. Similarly sigma n, the normal stress, that means if you look at the cross section, you know, so suppose this is the cross section, okay. So these stresses or the force which are trying to cause these things to means break apart, so those are normal to these forces, these surfaces, these areas, and that is why this term normal, okay, normal stress. So force per area which is normal to these forces. So this area A1 is normal to the force that is trying to break it apart. So that's what is the sigma n1 and sigma n2 if I want to write. So this will be F2 over A2. So that's how you define the normal stress, and I'm quite sure that in your 12th standard you have used these stresses only, and you never bothered to call them as normal stress or something, you just call them stresses because no other types of stresses were generally involved in your problem solving. Okay. But now onwards we will be talking about these kind of stresses as normal stresses. Then what was there in our list? It's the shearing stress, and I'm quite sure that you also have studied something about the shearing stresses in your 12th standard. Now just try to see or think about the pin which is now holding all these things together there, okay. If I try to draw a closure look at the pin, you may think that sometimes, you know, let me try to draw the pin first. Say here it's a pin, okay, and then you put say a nut there somewhere, so that it to keep it there, and similarly here maybe. Okay, it's an hexagonal nut, and then what I'll do is maybe from this side one rod is coming like this, and from the other side should I do them, because otherwise I'll make them flush here, okay, very close to this thing. And similarly the other one maybe of this type, okay, so like that. And suppose you are applying a force here and a force here, okay, and just think about this, and so these kind of joints are actually used at the joints in these trusses, okay, sort of. If you look closely, you may see something like this, and about this pin, these two rods are free to rotate. So that's how the structure is roughly, okay. Now if that is so, then if I pull like that, don't you think that this pin will have a tendency to shear off, okay, at this area of cross section, for example this one. So this part is the more vulnerable area where the pin is will have a tendency to shear off. So that's how any time when you, so the general condition of a shearing force being developed is you have a material like this, and then you have something like this. You are applying a force here with a cutter like this, and maybe another one which is very close to this, okay, and here it is. So in this way, okay. So here I'll draw it, you know. So there is a very, it's like that. Now if you apply force like this material will have a tendency to slide across this cross section. Okay, so this is called shearing, and the same situation is happening here. So that's the general schematic of where a shearing force will be developed, and here it's a situation with a pin joint, okay. And then this area of cross section I'll write, say, as A, area of cross section of the pin joint is the area responsible for creating the stress. For example, here generally we represent shear stress as tau, okay, and tau, I'll say write S also, but generally it's not required. Tau means generally shear stress, whatever. S is for shear, will be equal to say this F over this A. Now if you compare this equation with the other one, the formula is exactly the same, force per area, but the difference is this force is applied on an area which is in the same plane of the force. See this force is in the same direction of the plane, or it lies on the plane in a way, okay. So the normal to the area is normal to the force, as opposed to this case the normal to the area was in line with the force. So that's the difference between the normal stress and the shear stress. And then so these are the two things, and then what was the third one in our list is the bearing stress, okay. Now what is that? If you look even closer at this location, you will see that I'll just try to draw this, and at this surface, you know, you will have, say, something like this, okay. So this end I am trying to draw, okay, and so something like this. Okay. So and then I have cut it from maybe from this location. So from here somewhere I have cut it to show you that how it looks like, and then this pin sits here, okay. So this is the pin which comes and sits here, and then when you apply this force, this surface, you see this surface, so this curved surface is in contact with this curved surface of the pin, and it is trying to press it, okay. A compressive force applies on this, and in turn, in reaction, this pin applies a compressive force on this one. And if you see the area, the effective area on which this whole thing acts is, if this height is say T, and if this diameter is say D, and then the bearing stress, which is like a normal stress because the force is applying is getting applied in a way normal to the surface. So we will say that the sigma, again we are using the same letter sigma because it is more like a normal stress than shear stress. So here I will write say it is B for bearing stress will be equal to say this force which was acting divided by this area now, which is T times D. This is the projected area, not even the curved area, but it is the projected area because that is what is the that is what is responsible for taking this bearing stress. So these are the three types of stresses which I was talking about: the bearing stress, the shearing stress, and the normal stress. So primarily these are the three kinds of stresses which we will deal with in all our discussions. Anything else I wanted to do? I think yeah. So that's it for this segment, and then we will get into the axial loadings because now we have at least the least vocabulary to talk about stresses that can come up in the discussion of axial loading. So see you in the next segment.